Right now, gravity is not pulling you toward the Earth. I know that sounds insane. You can feel it. Your body has weight. Things fall. But here's the uncomfortable truth Einstein proved over a century ago. There is no force pulling you down. None. Zero. And the fact that you're sitting there feeling pulled right now means your brain, and honestly your entire sense of reality, is being fooled by the shape of space itself.
By the end of this video, you're going to understand why apples fall, why the moon doesn't crash into us, and why astronauts aren't escaping gravity on the ISS. They're actually falling forever and missing the ground. You'll see the exact 17th century assumption that Isaac Newton got wrong, the thought experiment Einstein used to fix it while sitting in a chair, and the one experiment in 2015 that finally proved space itself can ripple like water.
And right at the end, I'll show you the terrifying part. Gravity is the only force we haven't been able to explain at the smallest scales of the universe, which means something about it is still fundamentally broken. This isn't fringe theory. This is the framework behind GPS satellites, black hole imaging, and the 2017 Nobel Prize in Physics for detecting gravitational waves at LIGO.
Physicists have bet their careers on this being right. Let's find out why. Here's a question almost nobody asks correctly. When Newton supposedly saw an apple fall, what was actually strange to him? It wasn't that the apple fell. Everyone in 1666 knew apples fell. What stopped Newton cold was a much weirder idea. What if the same force pulling the apple down was also the force keeping the moon from flying off into space? Two completely different looking events. A piece of fruit dropping 3 feet and a giant rock orbiting Earth for billions of years, governed by one invisible rule. Newton wrote the math. Force equals mass times mass divided by distance squared. It worked. It predicted planetary orbits. It sent rockets to the moon 300 years later. But here's the catch nobody tells you in school. Newton himself admitted he had no idea why gravity worked.
He called action at a distance, one object pulling another across empty space with nothing touching it, philosophically absurd, even as he used the math to describe it perfectly. That why sat unanswered for 250 years. Then, a 26-year-old patent clerk had a thought so simple, it's now called the happiest thought of his life, and it broke gravity apart completely. What if you couldn't tell the difference between falling and floating?
In 1907, Einstein imagined a person standing in a sealed elevator in deep space, far from any planet, being accelerated upward by a rocket. To that person, it would feel exactly, indistinguishably like standing on Earth. Now, imagine the cable snaps and the elevator free falls. Inside, everything goes weightless. Pens, keys, the person themselves, floating perfectly still, as if gravity had simply switched off. Einstein realized it had switched off. Free fall and floating in empty space are the same physical state. There is no experiment you could run inside that elevator to tell them apart. This meant gravity wasn't a force at all. It was something about the space the elevator was sitting in. If falling feels like nothing, then maybe falling objects aren't being pushed by anything. Maybe they're just moving in a straight line through a version of space that isn't straight anymore. Which raises the obvious question, what could possibly bend empty space? The answer took Einstein 8 more years, and it's stranger than fiction. Picture a bowling ball dropped onto a stretched trampoline. What happens to a marble rolled nearby? It curves toward the bowling ball, not because the ball reaches out and grabs it, but because the ball has warped the surface the marble is rolling across.
In 1915, Einstein published General Relativity, arguing that mass and energy do exactly this to the fabric of space and time itself, a single four-dimensional structure called spacetime.
Earth doesn't reach out and pull the moon. Earth's mass dents spacetime, and the moon is simply traveling in the straightest possible line through a dented surface, a path that happens to curve into an orbit.
This is why the theory made a prediction Newton's model never could. Light, which has no mass to be pulled by anything, should still bend when it passes a massive star, because it's the space itself doing the bending.
In 1919, astronomer Arthur Eddington photographed starlight bending around the sun during a solar eclipse, exactly matching Einstein's number. Overnight, Einstein became the most famous scientist alive. But a warped trampoline is easy to picture sitting still. What happens when massive objects don't sit still? When they collide? In 2015, we found out, and it nearly broke the most sensitive instrument humans have ever built. Can empty space physically shake? Like water in a pond? On September 14th, 2015, two black holes 1.3 billion light years away collided and merged, releasing more energy in a fraction of a second than every star in the observable universe combined, as gravitational waves, ripples in space-time itself, traveling outward at the speed of light. By the time that ripple reached Earth, it stretched and squeezed the fabric of space by roughly 1/10,000th the width of a proton. The LIGO detector, a pair of 4-kilometer laser tunnels built specifically to catch this, measured it. It won the 2017 Nobel Prize. That detection didn't just confirm Einstein's math. It proved space-time isn't a passive backdrop for the universe. It's a physical thing with its own texture that can bend, stretch, and ripple like a material.
So gravity isn't a mysterious pulling force, it's geometry. Case closed. Except for one enormous problem physicists still can't solve, and it's the reason gravity might be the strangest force in the universe. Here's the part that keeps physicists up at night. Every other force in the universe, electromagnetism and the strong and weak nuclear forces, has been successfully described by quantum mechanics, the rulebook for how the universe behaves at the smallest possible scales. Gravity is the one holdout. The moment you try to zoom into gravity at the scale of a single particle, Einstein's smooth, elegant geometry breaks down into nonsense. Infinite numbers, undefined results, equations that simply stop working. This isn't a minor gap. It means the two most successful theories in the history of physics, general relativity and quantum mechanics, are right now mathematically incompatible. And the one place where you absolutely need both at once, the center of a black hole, or the first instant of the Big Bang, is a place our current understanding of gravity cannot describe at all. Every falling apple you'll ever see is fully explained. But zoom in far enough, and the theory that unified the cosmos quietly falls apart. Next time something falls in front of you, a dropped phone, a spilled coffee, a leaf off a tree, you're not watching an object get pulled. You're watching it travel in a perfectly straight line through space that Earth has bent around itself. Nothing is pulling anything. The floor beneath your feet is the only thing in this entire story actually pushing on you. But if gravity is really just geometry, a shape, not a force, then black holes aren't cosmic vacuum cleaners sucking everything in. They're something far stranger. A place where space-time folds in on itself so completely that every straight line leads to the same point.
click on this video right here, where I break down what's actually inside a black hole and why the math says time itself comes to an end there.